Welcome.
Thank you.
So I know a lot of people don't have Mathematica Home Edition or the full-blown version yet. And I had hoped, like I mentioned in the last meetup, that the cloud version or Wolfram language would have dropped already. And I know it's about to because I just got pinged to do my renewal of my license. And in the email from the lady, she said, you know, we want to make sure you get Mathematica 10 and all the new stuff that's coming out. So I know it's ready to drop. And she said it was a few weeks. So any week now, it's going to drop out and we'll have it. I was hoping it would be before this meeting because more people might have it to try stuff. But unless you have a Raspberry Pi, you probably don't have Wolfram Mathematica. Most people don't want to drop $300 on the Home Edition either. So, or if you're a student, you can get it for $99, right? So if you're a student, take advantage of that. Pretty good. But anyway, what I have here is Mathematica 9. Who's looked at Mathematica recently? Anybody?
I have not.
Okay, so I'm gonna do something and play one of the videos, right? And I might play a lot of videos just because nobody's really got it here. And it's gonna be able to show us stuff and then we can branch off from there. So some of these you can find on the web yourself, but the idea with the meetup sometimes, especially like this style, is it gives us a time 1 hour a month or 2 hours a month to actually just focus on one thing. So, you know, give me feedback because I'm still learning all this stuff, like I said. So sometimes the videos are going to be the quickest way for me to introduce something and then go off from there, or the documentation. And I'm still learning a lot, so I don't have like a ton of example programs to show because I'm still learning the programs, the language. That being said, there's one other thing I brought that if you're really going to get into this and you want to learn and use it as a tool, but you're not a programmer, but you need to program it, this is the book to buy. This is the most up-to-date one. The guy who wrote this worked at Wolfram for like 18 years, and he was in charge of writing a ton of their documentation. It's all glossy paper, full color, and he goes like, he covers all kinds of different problem areas, so regardless of who you are, you're going to see something in here that's going to be relevant to you. But he starts out with the basics of like how you use the notebooks to enter stuff. And there's questions at the end of the chapter for you to write little programs. And most of the little programs you write are like less than 5 lines of code. But you can download all the answers, right? And as we look tonight, I'll show you ways that while you're downloading stuff, you'll be able to look up the documentation and see how things work really super easy because of the environment. But it goes all the way through doing image manipulation, 3D plots from, if you download some of the geographic data from the US government, it's got the altitude data in here so Mathematica can plot it in full 3D. And it's basically like a line and a half of code to do. So this book it covers the graphing stuff, the different approaches to programming, whether it's procedural or functional or pattern match. Those are 3 different major ways that you can approach a problem in Mathematica. So this is like the book to get. The other one is the O'Reilly Mathematica Cookbook. You can get the ebook version of that one. This one doesn't have an ebook version, or I would tell you to get that, because this is like $89. But it's worth it if you're going to do Mathematica. But the O'Reilly Cookbook is from version 8. Anyway, it's got all kinds of little cookbooky kinds of things in there where you can go in and you can just do, you need to do that one thing, it's got the little kind of recipe and you can learn enough to. So for you, that's going to be really relevant. But this has got a lot of that too, just when you're flipping around. So I'd say those are the 2 books that are out there to buy straight off the bat and just have on your shelf as a Mathematica user. And then the other thing, Mathematica's documentation is unsurpassed. There is no programming system I've ever seen or system I've ever seen that has better documentation. So I'm going to show you that real quick. There's two ways to get to it. When you first start up in Mathematica, it'll bring up this. And this is kind of your little launcher, right? You can create some notebooks or slideshow or some other things, programs and libraries. Shows you the ones you used to already have open. And then it's got these things. These up here are kind of the current things they want to point out to you that are important in this version of the system. And we'll look at some of those in a minute. The documentation. Find your own learning path. I'll bring that up in a second. Demonstrations with source code. Those are really, really cool. And not only are they cool because you can go in there and see like 10, 20,000 things that other people have done, but for every single one of them, you can download the source and see exactly how they did it, right? And then change it, make your own, and then upload your example. Then there's the community, which is like forums and bulletin boards back in the day where you can ask questions, get help from other Mathematica users. That's turned out to be really good. I haven't had to ask any questions yet because there's been so many answers in there that helped me already. So it's like, this is your launch pad. If you happen to close this window, you can always get back to it by going to your help and going to welcome screen. And on the Windows box, it's the same way. There's a help menu and you do the same thing. So documentation-wise, I'm going to pull that one up. And these are all things I consider intro to Mathematica, important kinds of things. That's why I'm going over them. But this is the documentation center. Mathematica used to have this really big book. It was like 3 of these thick, right? And that was for Mathematica 5. If you were to print all that stuff out now, it's going to be like this thick for all the Mathematica documentation, both sides. Really thin paper. That being said, I'll show you in a minute. You can actually go and get every little section of every book of the entire Mathematica documentation as a PDF that you can download and put on your Kindle or whatever. Or you can just read it from here, right? This goes to the web version of it, but if you want PDF or offline access, you're good. And I know some of those will be obvious when you get your own copy of Mathematica or when you do the Wolfram language on the Raspberry Pi, it's there too. Getting started really is getting started. It's going to take us to our first video, and I'm just going to play this video because it's going to say a lot of stuff I could say a lot quicker because they added it and they won't ramble like I tend to. So. Hold on. Audio is supposed to go through over there. Let me fix it. They were dorking with the settings when I came in. So let me change it all. Yes. Excellent. Let's get it.
More. It's the only development platform fully integrating computation into complete workflows, from modeling to simulation, visualization, development, documentation, and deployment. Mathematica is built to help you with all of your technical tasks, from performing daily computations to designing large-scale, innovative solutions. Millions of people worldwide, including Fortune 500 companies in every industry, use Mathematica to gain a competitive edge. You'll find Mathematica at work in industries including financial modeling, aerospace engineering, medical imaging, social network analysis, and industrial robotics, to name a few. Mathematica is one integrated system, eliminating the need to buy, learn, and maintain multiple tools and add-on packages. This dramatically decreases both your costs and time to market. With Mathematica, you can program the way you think, including using free-form linguistic input. And you can build on your results faster using Mathematica's state-of-the-art input assistant and suggestions bar. Using unique hybrid symbolic numeric computation, Mathematica delivers results of unmatched reliability and precision. It solves problems other tools cannot. With Mathematica, you can get results faster thanks to thousands of highly optimized algorithms and built-in support for parallel computation and GPU architectures. Underlying all of Mathematica is automation at every level, dramatically boosting your productivity and output consistency. Mathematica also connects to all your existing applications and databases, allowing you to build on your existing work and infrastructure. Effortlessly deliver your content and applications cross-platform using innovative technologies like computable document format. Built ground up for more than 20 years, Mathematica is the ultimate technical application and development environment. Start learning how Mathematica can give your innovation a cutting edge today.
Okay, so we had the sales.
Mathematica 9 is a major new version of the world's leading computational software.
This particular video, I can't understand why it's not going full screen. Oh, there we go. Good. So this one is just going to show you what's new in Mathematica 9. This one's really long, so give you an option. You can watch this on your own on their website, right? Wolfram.com, right? And we can look at a couple other things, right? We would rather do that.
What would you rather do?
I would like to show you things because you can watch videos. I want to show you that the videos are there. And there's some that I want to show you, and then there's some like this one where it's kind of just showing you features, right? So, but unlike the closure group where we always have speakers and stuff, this one's supposed to be more interactive. Yeah. So that's why I'm asking.
Well, are we gonna, if we don't see this now, or are we gonna understand what you're talking about?
Yeah, because that's new features. I'm going to show you some of the just the basic core stuff, right? Yeah. It'll be applicable. The big deal is when you click on from the main. If I just go to wolfram.com, right? And this is what you could do. You can go here, and this is their new site, right? And they have it organized slightly differently than they used to, which is kind of good. So you can see about the Raspberry Pi here, the Wolfram language, APIs and Instant, their blog. So they've got it organized by like the latest news. So as you scroll down, these are older things, right? But they're topical. Then you can go back up to here and you can choose which product, right? In this case, we're talking about Mathematica, but programming in the cloud is one of the other big announcements where everything you do in Mathematica on a desktop will be in a browser. So you can full access to Mathematica to your web browser. It'll just be calculating on their servers and stuff, right? And they haven't announced pricing for that, so but it's worth looking at. But anyway, when you come in here to Mathematica through just products and services and go to Mathematica, you can get to all these things with the videos and just click on what's new, and you'll have some links to each one of these you can link to, and they'll have some videos and other stuff associated with them, right? So that's the easy way to get to that. So we'll come back to here, go to this getting started page again. So when you go from inside of Mathematica, you can go and get to these same videos, what's new, suggestion bars, context sensitive help. I'll show you those things in just a second, but the other important things are when you're in, if you go into support, there's this thing called Learning Center. That's got a ton of really good stuff in it. Specifically, you can get to the documentation, but these videos and screenscasts are what some of the things I was talking about. If you've already seen Wolfram do his demo at South by Southwest, that's really cool. There's a really short version of it here that's 12 minutes long. Has anybody seen that?
The short version?
The short version?
I saw the South by one.
Okay, so I'm going to show you that one because that's going to be what this group goes forward with. Probably the next meeting, I'm thinking that it will finally be announced and all the pricing and everything will be talked about. But this is what, if you buy a Raspberry Pi for 35 bucks, you'll be able to do all that this video shows you and more. So I'll show you that, and then we'll jump into a couple of the other things. Because this one is...
Hi, I'm Stephen Wolfram, and I'd like to show you a bit about our Wolfram language. You know, I've been working towards what's now the Wolfram language for about 30 years, and big parts of it I've been able to incubate in Mathematica and Wolfram Alpha. But it's only in recent times that we finally had what we need to create the whole Wolfram language and to set up mechanisms to deploy it very widely. We're actually at an incredibly exciting point right now where we're suddenly able to take computation to a whole new level and, in effect, inject sophisticated computation into everything. So what is the Wolfram language? Well, the first thing to say is that it's a new kind of thing. It's what I call a knowledge-based language. It's a language where a vast amount of knowledge about how to do computations and about the world is built right into the language. So right within the language, there are primitives for processing images or laying out networks or looking up stock prices or creating interfaces or solving optimization problems or whatever. And through the symbolic structure of the language, they're all set up to work together in a wonderfully coherent way. Let me show you. One of the great things about the Wolfram language is that if you want to, you can use it completely interactively, even on the web. So you can type something in and immediately get a result out, like this, or like this. Yes, it's fast. Of course, it knows how to factor that number too. It's got all the fancy algorithms built right in. It's also got immediate visualization. It also knows right off the bat, like, how to get your friend network from Facebook. It lays out the network automatically, and it knows all the fancy graph theory algorithms. So you can immediately ask it all kinds of things about the network, like, how do your friends break into groups? Or what's the most connections any friend has? The Wolfram language knows how to do lots of things, like, let's ask it to get the current image from my computer's camera. Ah, that's me. Well, let's, like, edge detect me. I can have it be dynamic, too. I can do all kinds of computations, like, there's me broken into little squares, and there's me with a random color blended into each square, and now reassembled. The Wolfram language doesn't just know about algorithms and computations, it also knows about the world. Like, let's ask it when the sun will set today. There's the answer for my current location. There's the time from sunrise to sunset in days. We can convert it to minutes. You know, the Wolfram language has a precise way of talking about everything, but when we're dealing with the world at large, we often just want to use natural language to describe what we're talking about. And thanks to Wolfram Alpha, we built a big stack of technology for doing that. Like, we can just ask for countries in South America, and our natural language understanding system can figure out what that means and generate precise Wolfram language code from it, so that we get a list of the countries. And now we can compute from that. Like, let's generate their flags, or let's find the dominant colors in those flags, or let's have a whole little program to make a table of countries and their dominant flag colors. Okay, let's try something more ambitious. Let's get a list of the capitals of the countries in Western Europe. Now let's find what order we'd have to visit these in to have the shortest tour of all of them. Needless to say, the Wolfram language has the best known algorithms for solving a so-called traveling salesman problem like that. Now let's plot the tour on a map as a thick red line. And yes, the Wolfram language has detailed maps of everywhere built in. Okay, well, I've been doing different kinds of examples. There's really a huge amount built into the Wolfram language. You can get a sense of it here. Thousands of algorithmic functions, thousands of domains of data and knowledge. But in a sense, that's just the beginning, because there's so much more power from being able to put all these things together. And what makes that possible is the structure of the Wolfram language and the principles that it's built on. The first really critical thing to understand about the Wolfram language is that it's symbolic. If you have x, you don't have to give it a value. You can just have it be symbolic x. You can type in a formula involving x, and then you can do a computation on the formula symbolically. And of course this is great for math, but one of the big discoveries of the Wolfram language is that it gives you a way to do a zillion other things too. Let's say you've got some data with a part you don't know. You can just treat it symbolically. What about something like a network? Well, in the Wolfram language, it's a symbolic expression too, that displays as a graph, but you can go ahead and manipulate it symbolically too. Same with 3D graphics. Go ahead and create a symbolic form, render it as 3D graphics. Now, because everything is symbolic, I can just pick up this output and say feed it into an image processing algorithm. Or I can make a table of rotated versions of the image. Something else that's a symbolic expression in the Wolfram language is a user interface element, like a slider. I can make a whole grid of them, build up any user interface, all just represented by a symbolic expression. Same with documents and document elements too, all just symbolic. And once things are symbolic, it's easy to do meta operations on them, like take a plot and effectively just pick it up and make a dynamic version of it. You can make a dynamic version of anything. And because everything is a symbolic expression, it all just works. You know, any function can be treated symbolically. Here's just f, symbolic f. And actually, underneath, the full form of everything in the language is like this. Just a bunch of symbolic functions, representing formulas or data sets or documents or cities or whatever. So, what can you do with these symbolic functions? Well, one thing is incredibly powerful functional programming. Nest a function symbolically, or put more and more frames around something, or make a kind of nested interface. Okay, here's something more ambitious. Let's use functional programming to do some web crawling. The Wolfram language already knows how to import lots of things, like hyperlinks from my website. It's a little more code, but let's nestedly crawl out a couple of levels, then make a graph of what that corner of the web looks like. You know, you can make symbolic pure functions to do all sorts of things. Like this takes the list of English words that are built into the Wolfram language and creates a function to find which one is nearest to a given word. Now you can pick up this function and apply it to any word and make a simple spell corrector. Pure functions and functional programming get in everywhere. Here's selecting palindrome words based on a simple symbolic pure function. You can generalize this dramatically and, for example, get a shockingly powerful symbolic way to query databases and large hierarchical collections of data. In a sense, the Wolfram language is kind of the ultimate fusion language, because its symbolic nature lets it encompass pretty much any style of programming. One that's very powerful and kind of uniquely symbolic is pattern-based programming. The idea is you give a pattern for transforming some class of symbolic expressions. Like this says that any time there's f of some particular nested list structure, here's the value. So now if we give f this kind of structure, it'll produce a result. But if the pattern doesn't match, it'll just stay symbolic. And this is basically how all function definitions in the Wolfram language work. The Wolfram language is a huge language, by far the largest ever, but it's built on a small set of powerful principles. The first is coherence, the idea that everything in the language must fit together. I must say that I've spent a fair fraction of the past 30 years working to make this happen, designing every corner of the language so it's as consistent and unified and integrated as possible. So it's easy to understand, and so one can take something from over here and be confident that it'll feed right into something over there. I've had another principle too, maximum automation, the idea that the language should take care of as much as possible. Let's say you're doing machine learning and you want to build a data classifier. Well, there are all sorts of methods for doing that, but in the Wolfram language there's just one superfunction, classify, that's packed with meta-algorithms to automatically figure out what to do. Of course, if you want, you can go in and control every detail, but otherwise you can just treat it like a black box, one of thousands of superfunctions in the Wolfram language, that effectively give you the highest possible level building blocks for programs. And these building blocks don't just contain algorithms, they've got knowledge and data too. Knowledge about how to import and export hundreds of formats, knowledge about how to interact with all sorts of external APIs, knowledge about how to compute properties of systems in the world, and also huge amounts of curated computable data stored in the Wolfram cloud and continuously updated. The same data that powers Wolfram Alpha, completely programmatically accessible. But okay, so the Wolfram language makes it really easy to create really powerful programs. But what can you do with them? Well, it turns out that the symbolic nature of the language does something great here too, because it lets the language define and describe its own deployment. Let's say you set up a function in the Wolfram language. You can run it in your notebook session, or you can just take the symbolic code and deploy it to the cloud. You can just go to the cloud object from the web, and if you do, you'll see a web interface, which automatically runs your Wolfram language code in the cloud. And by the way, you can set up a mobile app to do the same kind of thing. The interface here uses CDF, our computable document format, running in the cloud. And in fact, you can run the whole native notebook interface for the Wolfram language in the cloud. Here it is. You can use notebooks as templates for reports that get filled in by running Wolfram Language code. You can schedule Wolfram Language code to run on cloud servers at particular times, say sending you mail. You can take any Wolfram Language function and set up an instant API for it that you can call from anywhere on the web. Like this asks for a JSON output of some weather data for the user's geolocation. If you have an embedded Wolfram engine, you can get code to embed a call to this in lots of languages. And you can actually call the code without even going to the web. One thing about the Wolfram language is that it's completely scalable. You can write tiny one-line programs that are already very powerful, or you can write multi-million line programs like Wolfram Alpha. It's so much easier to build and debug symbolic programs because at every stage, every piece is meaningful. And depending on your style of programming, there are various IDEs for the Wolfram language that take advantage of the symbolic character of the language. You can use the Wolfram language for high-performance computing, too. It's got parallelism built right into the language. So this is automatically starting up and running lots of different processes across my little heterogeneous network and collecting the results. You can also use the Wolfram language on the upcoming generation of tiny embedded processors. And for example, it's included with the OS for the Raspberry Pi Linux computer. You can use the Wolfram language to interact with devices. In fact, the Wolfram language is in a unique position with respect to devices and with respect to real-world data in general, because in a sense it's a language that has a model of the world built in. And in fact, WDF, the Wolfram Data Framework, encapsulates that model. And within the Wolfram language there are lots of ways of taking unstructured data and getting it into WDF, with its units and dates and entities and so on made canonical. When it comes to devices, the Wolfram Connected Devices project is curating them to make them automatically accessible from within the language. Okay, so I've tried to give some indication of what the Wolfram language is about. So how can you get started? Like after every output, there's a suggestions bar that suggests what you might want to do next. And you can even try just giving input in natural language and starting to construct your programs that way. And when you've got a program you like, you can deploy it in all sorts of ways. My goal with the Wolfram language has been to encapsulate as much computation and knowledge as possible, so people can go from ideas to deployed products as quickly and easily as possible. I've also been very pleased that the Wolfram language seems to be uniquely good as a first programming language, because you can do so much so easily and quickly get exposed to such a broad range of methods and topics. I've been working towards the Wolfram language for 30 years. We laid strong foundations very early, and we've just kept on building. And actually, I keep on being amazed at what's possible. And now we've got a vast stack of technology and content that I think just completely changes how we should think about programming. I get a big kick out of using it every day. I hope you'll have a chance to try it, and that you'll end up doing amazing things with the Wolfram language. Thanks very much.
Cool. So that kind of gives you an overview of the Titanic world that you're stepping into, right? But all those things are built on like a core set of ideas, right? The pattern match, the basic functional things. And you saw those little one-liners, right? So it's that video is what made me want to start a group. Because I had Mathematica on my own, and I was like, I could do all this. But then it was like, okay, now they're actually expanding it to it's going to be something that lots of people can use. You can write a little utility and expose it for people on the cloud, and other people can hit it, right? So the other thing is, Wolfram language adds those devices in. You can read and write from I/O ports on a Raspberry Pi, right? So that little thing with the potentiometer on that breadboard, that actually already works, right? So you have that going and feed it into Mathematica, plotting the graph in real time, and changing the LED brightness and all that. So Mathematica as a language for solving problems, there's nothing really quite in its league anymore. The closest thing I saw before that was a small fucker Lisp system. But so I'm like super excited, but at the same time, there's so much stuff. It's like somewhat overwhelming, right? So that's the video. There's a couple other ones on there that talk about the cloud that you can go to. I'm not going to play those. But anyway, I'm going to go go back to the support overview and back to these videos and screencasts, because there's some other good ones that are in here. There's multiple channels over here which are kind of important that you can learn about. This getting started in Mathematica is a really good one, but the feature videos is always kind of cool too. Those change a lot. This is really cool stuff there. But then you can go in these channels, and this getting started is good. There's the Wolfram language one. Grid Mathematica is, if you write a program in Mathematica and you parallelize it, Mathematica will automatically put it on as many of your boxes that you have the Mathematica runtime on. And it'll automatically deal with all the data movement, all that kind of stuff, right? So Grid Mathematica gives you a little front end, and you can monitor the individual compute boxes. And so what we hope to do is, if enough people actually get Raspberry Pis in the group, we're going to try and network them all one day, and then let them compute on one problem and try it out, right? Because when you get Mathematica, it'll take advantage of as many cores as you have, right? Like the commercial version, you can have 8 parallel things running at once, right? One for each, like on my laptop, it's one for each hyperthread, right? So I can have 8 parallel processes going on. But if we had, like, as the group grows, maybe we'll have 36 people, we could get a little router with 36 ports. And everybody, and we just feed in one Mathematica program and feed it some big data. Now, Raspberry Pi is like 100 times slower than one of these, but with each one of them having 512 mega RAM, it gives you some pretty interesting stuff. Or maybe create a group project where there's like a little game and the ball moves between the different Raspberry Pis or whatever, and you see it on your notebook or whatever, right? So there's just really no stopping the possibility.
So is this something that is already basically embedded in a lot of Python frameworks? Like maybe in a virtual machine format where you have different users accessing Mathematica through a Python framework for very dynamic type?
There's 1 or 2 Python linkages to let you call Mathematica to do computation, but they're not really that widespread, right? There's another one that uses Clojure to talk to Mathematica. That being said, with the Wolfram language, one of the things that he didn't show in this video, but he shows in another one, is when the Wolfram language comes out, you're going to be able to take one of those cloud things that you deploy and tell it, I want you to generate a calling program in Ruby or Python that will call this for me. And it'll give you that little stub, and if you're a Python programmer, you can take that little stub and then hook that into your Python front end. Let's say you're using Django or whatever, and you want to call the Mathematica backend to do your computation and then render a graph.
So it doesn't have to be embedded. It just
doesn't have to be embedded.
Whatever data set that you want to work with.
Right, you can run it on the server and let it do that. You could run it on the cloud version. If you want to do an embedded one, that's like if you're building a solution, you need to deploy a box somewhere and you want to have Mathematica as a core because you're doing big calculations or something, you can license that. But it's a license,
but if
right?
everything's cloud-based, you wouldn't want it embedded, is what you're saying.
Right.
You just want it to be able to communicate.
Yeah, right. And and there's trade-offs there. Maybe it's an intranet, right? So you may embed it, you may license it, the full-blown Mathematica, or you just may have one copy of the full-blown Mathematica, and then you have the embed engines that you can deploy in a grid, right? And you sell, like if you made your own appliances or something, you could do something like that.
Right.
But then you get into, because this is commercial software, you get into licensing, right?
You'd have to license it, right?
Right. And so that's the thing though, with Wolfram language, we don't know what the licensing is going to be, and they're trying to get it to as many people as possible. Like when you buy a Raspberry Pi, it's free, but it's free for non-commercial use. Right. So who knows what the licensing is going to cost for cloud and stuff like that. But again, it's one of those cases for what you get, try and write that on your own. It's going to be way cheaper to just pay a license fee, right? I think some of that
Is it
stuff.
possible for like 2 users to work on, I guess, the same project at the same time?
Yeah, and I'll show you.
Or 3 or 4 users? Or?
Yeah, let me go back into Mathematica and I'll show you kind of a single user version of how you would work with something. And that's going to be this idea of a notebook, right? And he kind of showed you something on the screen there that you saw a minute ago. So you just can enter your code right in like this, and you hit shift return and you get your output. So that's a notebook, and then the little suggestions bar pops up. You can see it up there, right? What are the divisors of 8? Let's click on that, and it'll show us all of it. Yeah, greatest common divisors, least common, whatever, right? So we've got that kind of stuff, and it's just saying which functions are applicable to this kind of structure that we've got back, right? But this is where you're exploring a problem, right? You have an idea, and we just wrote Mathematica code. I mean, if you look at that thing, divisor, I can right click on that, and I can say get help. And that's actually a function in the system. And right away, it takes me to the documentation for divisors, right? And I can see details about divisors. It takes n, and then it'll use Gaussian integers as the default divisor space to look in. So it's going to be integers in the Gaussian kind of expression space.
And then you could modify that?
You can modify that, and that's what's great about the documentation. Every piece of the documentation will always have these sections. It'll have details and options, examples, see also tutorials, and related guides. And I'm not kidding you, there's like hundreds of thousands of these things, and you can go off like, I went off one day and I was like 70 links in of like exploring stuff, and
Way out on a
then I'm
tangent.
like way back. Yeah, it was like, where did I start? I can't remember.
It was
But-
fun exploration, right?
Right, exactly. So like in this case, you can literally copy this code and bring it over into your notebook and click and paste it and hit shift return, and boom, you've got the same answer that they show in here, but you got to try it yourself, right? You can go in here and change the number, to something really weird like that. And boom, just replaced it in place, right? And you can see how fast that was. But then you've got the scope here, right? If you don't put anything here, give me all the divisors of 6 plus 4i. So it's going to do imaginary numbers here, right? And give me all the imaginary divisors, which from a math point of view is pretty cool, because doing that by hand is a pain in the ass from what I remember. In this case, it's showing us some options. We've got 3 basic options down here. Applications. Where does this make sense? Find all the perfect numbers less than 100,000, right? And here's the little program for doing that. And I'll paste it in here and we'll run it. And it's super fast, but basically what we did here is we said for the range of 10 to the 4th minus 1, right? Give me the divisors of the first value out of that range. And if it's equal to 2, then we're going to total that, right? And then we're going to select those guys, right? So actually I read this, there's a bracket there. Sorry, I need to make my screen bigger. Actually, let me change the font, because I can bump the font size here for everybody and make it more readable, I think. Is that better for people? Or bigger? Bigger. Bigger is better. Okay, so yeah. So we're going to select everybody who is in the range 10 to the 4th minus 1, and we're going to total all the divisors in that range. And then we're going to select everybody who's equal to 2, right, in that grouping. Right? And this is equal to, I'll have to look at what this means. I can't remember what that is. But basically, we selected everybody who, in this range, their divisor does something with 2.
But where does it say multiply them and put them in the airplane?
That's the select, right? The select statement's doing that. Right. We can get help on what select means. It takes a list and a criteria, right? So the list is this first thing, and then the criteria, well, actually the list is, let's see,
It's the range.
list and then criteria. So there's 2 square brackets.
Yeah, so the total.
So it's the range, and then total divisors equal to pound ampersand. I'm not sure what that means. I'm still learning that part. But
Okay.
the gist of it is, for this particular thing, we get all the divisors that I'm guessing are their total modulus 2 or something like that. In that range is that value. But I mean, a simpler case of what select does that's not stretching our neurons is give me all the even ones out of that list. Right. So that makes perfect sense. Select makes perfect sense there. Here's a slightly different one. Let's see if we can infer out of this what the ampersand and the pound mean. So we want to select, here's our list, and then here's our criteria. It did, because I didn't change it for the whole notebook, yeah. Let me see. Presentation. Yeah, there we go. Now we're bigger. Cool. So here's our list, and here's our criteria. So this is going to be the element in the list, but the element in the list is greater than 2 times that element. Is that?
No, I'm just saying greater.
So 4, 7, and 6. Is greater than 2. Anything greater than 2. So 1's not greater than 2, 2's not greater than 2, 4 is, 7 is, 6 is, and then 2's not. So that's what it is.
Yes.
And then return that list as the result. Right. So that being said, let's select ampersand and say get help. Right. It's an and, but it's also a function. Right. So here, there we go. It creates a function to do that. So select on this list applies a function that is that number is greater than 2. So ampersand after is creating a function definition. So like in this case, we have a little function called f. Let's see how they call it. Use the function. We'll use f here. And give f an a and f a b, call it twice in a list, because squirrely brackets are a list. So we feed a into this function, and we get 3 plus a, and then 3 plus b. Right, because the function is 3 plus the input value. So this ampersand after just means take what was previously here, make a function out of it. The pound sign is just the argument. and then assign that to the variable f. That's the name of the function now. And now we can call f of a, and it substitutes a in there for the pound sign. So 3 plus a, and then when we call f of b, it substitutes b in for the pound sign. So if we go back up to here,
This notation.
yeah, well, it's definitely different. So, and this is a shortcut notation. I'll come back. There's a long way that we could have wrote this pound greater than 2. You can actually say function, square bracket, under bar, x or whatever, close square bracket equal, right? This is just a shortcut inside of there. You put the body and then the ampersand, and it automatically builds the function for the body, right? But you can actually do function like that. There's examples. Pound or pound 1, pound 2 let you reference the arguments, right? So here's the body. So let's say G equals f of pound greater than 3 or 4. Let's do 3. Right. So we have G, and now if we say G of A is greater than 3. So we defined a function, put it into G, and then we said G of. Now let's try something, since he stressed symbolic stuff in there, let's say x plus t to the 5th. T to the 5th plus x is greater than 3. So it did stay symbolic, right? So that's kind of cool. Now there's this other manipulate command. So let's say g of x plus t to the 5th here, where I do x from 1 to 10, and I can't remember if this is the exact syntax, but t from 1 to 100. See if I get errors. Oh, I did it. So what manipulate's doing in this case is we take a function that we wanted to evaluate, and then we tell it the two variables that we're going to vary over by giving them in a list. X is going to vary from 1 to 10, and it gave us x and t on here for this equation. So now we're going to start varying x, and it is true. 1 plus t to the 5th is greater than 3. Right, because we're doing g of x, right? So now if we do this, we slide it, it's still true. It's still true. It's always going to be true for t, right? Because t is always going to be positive. So if I change this to negative 99, reeval, we should be able to see some falses for a long time. Oh, there's a true, right? And we can expand these two little guys, and we can see that when that drops to below 0 is when it pops over, right? And we can also animate it, right? So that's manipulate for two variables. Right, so that's kind of wild. We could go back up here and change this function. We could change this to be sine of pound, maybe, right? And then do this again. And so now we actually get values that are actually changing in real time. So this number is greater than the sine of that number. So this, to me, even though we made a stupid equation that doesn't really mean anything, the thing that's cool here is it's all symbolic. We didn't have to choose, like you would in Python or any other system, something that we knew was a real value. we could play with arbitrary X's and Y's and Z's, and if we want to make them real at that point, right? So that was kind of cool. And at first it doesn't seem like that's that valuable, but as you get into it a little more, it's like, oh wow, I can treat my program itself symbolically. So as you get more complicated, your code actually can rewrite your code based on
So it's
what
basically
you
more
change.
adaptable and malleable than other
Yeah.
forms of programming.
Right. Because, like, I'm going to show you this. I'm going to do, here's another function that's really cool. I'm going to do head of G. What head does is it shows you what the thing you ask it about, what its type in the system is, right? So head of G gives us back functions. So G is a function, right, to the system. We can do attributes of G, and there's no attributes on it right now. So if you worked in any other languages or systems, attributes are things that you can add to. So I can add an attribute to G that's specific to my system metadata in a sense, right? Sometimes the system does have attributes, like if I say attributes of sign, right, as a function. So the sign function is a listable, it's a numeric function, and it's protected. And what protected means here is that we can't override it. Now we can change that if we want to dork with the built-in sign function, but I don't suggest it. Just say my sign or whatever, right? But anyway, you can see that there's metadata in the real system functions too, and those in this book it goes into that kind of stuff. Like, and you hit some of that stuff early on, but you don't get overwhelmed with it. They show it to you, and then later, as you work through more and more examples. Because this really is a book where you actually do. You don't just read it. Every like couple paragraphs, you're doing something. You're typing a piece of code in, you're gonna try it. And it's live. And then, you know, it becomes real that way. So one of the other things that he talked about was if you press the equal thing, you can say the English, states in Germany. All right. Are there states in Germany? Anybody? Anybody?
Yeah.
There are. So there they are, right?
Cool.
So that is the English input, the states in Germany. Now notice here, it gave us back the result is Mathematica list, right? So we see the result there, and then it put it out for us to work with that list here. But it shows us the English output, and then it slammed it into our notebook as a list. So we don't have to copy it. I don't have to go up into here and copy it down into here. It kind of shows us in both ways, right? And this is one of the things you can do. As you write programs and you want to have the system render something a special way for your data, you can give it an output format in the notebooks. You can tell it how to spit out your data so it's visualized the way you want to see it. You can build all that, right? Let's do like the current temperature. Hopefully it'll assume that I want it for where we are. And there's no result there because it doesn't know where I am. Oh, it does. 82. Right? So that actually went out. That goes out to Wolfram Alpha.
Right.
So as long as you've got a web connection, it goes out to Wolfram Alpha and pulls back whatever you want. Like, let's do another one. President.
Can you ask for a location?
Yeah.
Current location.
Now what this will do is it will, depending on your hardware, like,
Oh, wow. That's not so useful.
depending on your hardware, it'll use the IP address and stuff like that to give you that data. If you have hardware that will give you the geolocation and stuff, it can return that as well, right?
But there are lots of geolocation services.
Right.
Didn't bother.
So let's say,
Well, when it was showing the devices thing and what they're doing with, I guess accounting for all the devices and the Internet of Things. I mean, this has GPS and stuff like that. So
Right.
I guess in that sense, it would be good for geolocating devices all over the place.
Right. You think you're in France?
well, that's geo. It's probably a name, right? This is where like English is not a great input format for computers, right? And this is the deal. Like, have you guys ever used Wolfram Alpha? Have you gone to the site, played around with it?
Yeah.
It's kind of hit or miss on some things.
Yeah.
The reason is, it's not like a Google where they index the world. All they do is they curate large data sets from people, and they normalize the data, and they come up with what the most common names of the columns and the fields are. And as long as you type your question in and it knows a piece of data and you actually stumble upon the column name, it can solve it. And that's what he means by computable data. Computable data in Wolfram Alpha is data that is curatable. It's not random, it's not ill-formed, it's not just blobs of text, right? It has to be structured in some way or structurable, and that's what they do with it, right? And then you're able to use it, right? All the cities in a country, all the states in a country, all the provinces, those things are regular, and you can store them in a database and use them, right? So that's a lot of what Wolfram Alpha has in it.
And does that just update constantly, or is it only
Yeah, because
version by version?
every time you use those, you're hitting the Wolfram Alpha servers, and they're constantly curating the data. They literally like get data feeds in all the time, like
Right, from everywhere, just all kinds of
yeah, current MLB base games. Let's see if this. I think this one actually works. It did for NFL, so we'll see. And they actually get real-time feeds for stuff. So obviously it didn't know what I meant by MLB. Let's try one more thing. Current baseball scores. Let's do that. Since MLB is an abbreviation. The score of a baseball game. It's a noun. Thank you. Right. So, like, you can click this and give feedback, which I do all the time, kind of to help them increase their vocabulary, because that is like a normal thing somebody would type in, right? And they have a really nice way of doing it. The other deal is you can show all the results, right? Here it thought it was word data, right? So the score of a baseball game, it was trying to figure out, what that meant. So now, as a diversion here, I'm just going to go over to Wolfram Alpha real quick. You can do, like, there's examples here we can steal from, right? And you can go down here into sports somewhere, sports and games, right? So you can go into here, like, last pro baseball game with more than 9 stolen bases. So that's data that they have statistics for in a database. They have it indexed, and then it'll go out there and do its little work. And we
spent all that time.
Right. So, and the reason is because the data is denormalized, right? So it's computable. You can hit it from other data sources and join against it in a sense, right? So we should be able to take that same query, bring it over here, do the same thing with it. So hopefully that'll be true. Let's do equal paste. And maybe it'll even be in our cache and we'll get it back sooner. Boom, there you go. So we got that back. Now here we can see the results in the same mode. I just crashed it. We got it in the same output format that they did, right? So that was cool. So now I'm going to show you some other basic stuff that is going to help you if you buy your Raspberry Pi. Okay. When you type in something like x equals 5, right, and you hit shift return, it'll put the output, and the output's 5, right? So if I go down here and I hit x again, x has got the value of 5. So everywhere I dereference x, it's going to have 5. Now over here, if I want to delete these things, get rid of them, I can select these nested cells, right, with the cursor. Or I can use the arrow key to move up and down, or to the right, right, and down, right, to do my selections, right. Now, the option key does something, the control key does something, the function key does something. Anyway, so you move through these guys, right? But anyway, when you want to get rid of a section, like, I typically don't get rid of sections, I just leave everything as I'm going through the notebook, exploring and playing. But if you want to delete something, you just select that whole hierarchy, or you can select an individual cell, right? And then come back up here and type the shift return. This is kind of cool. Binary form of 5 is 1, 0, 1. Kind of cool thing. Number of primes less than 5 is 3. A range 1 to 3. You can do reverse them, give me the max, all kinds of crud there, right? And here, after you do that, you've done your exploring, and you want to collapse all that because you figured out what you want, and now you know how that one little chunk of code does what you want. You can click this and you can say preview it and roll up, and it'll roll that all up into this one little function, right? Give me the primes of x equal 5 for this range and reverse them all. So that one little function is everything I did to get the reverse there, right? So it's kind of nice as you explore, I figured it out. You don't have to go manually delete all that stuff like I showed you how to do. You can hit that one button and it does your nice stuff for you. So the other thing is, anytime you select an output, you're always going to get these things, right? You can click this to send it straight to Wolfram Alpha, and then you can send feedback on anything. They want feedback on anything, which is kind of cool because I don't know of many pieces of software that say, I'm going to give you the chance to give me feedback every single place we could screw up, right? Which was, I actually like that, so it's kind of cool. That being said, some other stuff you need to know. For beginner stuff. You can check your spelling, which is kind of cool, but if you want to do the input free form, control space, right? And it'll automatically do that equal sign for you. And you can say states in USA, right? So it automatically gives you that. Okay. And we've got that output, it's right there, right? So this particular thing is, this is a little module, right? And I can select this module and I can say convert it into its output form, right? Or I can say traditional form, right? And so far it's not doing anything. And we want to use that we'll say USA. So now it should know what we mean. Right? It's assuming those things. We can send translation back there. So more input is needed, right? So let's do this. Let's see if it's happier. Boom. So I was happy, right? So any one of these cells here, and that's what these are called, you can convert those into its traditional form, the raw input form, stuff like that, right? And when you're first getting started, that's not going to matter, but as you write Mathematica code, you're going to want some of the outputs to be in the traditional form because that's what you're going to need to use in your code as you go further, right? And in this case, this is just an output, so it's already in traditional form, which is a list of strings, right? So it's not really mattering there, right? You can do things like create a new graphic, and you can click on here, and you can see the drawing tools if you turn them on, and you can create your own graphics. Now, why was this matter? Because I can take this now and paste that into something and say sine, and now that's still symbolic. Now, sine of a piece of graphic doesn't actually mean anything, but again, it leaves things symbolic, right? Everywhere, right? So you don't ever have to worry about the equivalent of typecasting or that kind of stuff. If it doesn't apply, it'll leave it in the form it's in, because one of the things you may or may not remember in math from elementary school and Algebra 1, which is commutative property, right? Associative and combinatorial, or not combinatorial, but combining things, right? So if you have f of a plus b, right, is that the same as f of a plus f of b, right? And usually those would be true, right? Usually. There's some other math where it's not going to be true, just like there's weird geometry that's spherical versus 2D and all that crap, right? But the idea here is that you can punch anything. So we took this graph, we could take a picture from the internet and drop it in here of a globe or whatever, right? Now,
so in this instance, could you take the symbolic representation of that image and by some type of function or convert it into a different type of file, like an STL file or a
yeah, you can
file?
you could do export, right? And I think it's something like this. The first argument's not valid, but we can right click on export and get help and see that we need to give it a file. So we want to export it, we got to give it a name. So let's do this, we'll do it this way. I just have the arguments backwards, it looks like. I'll call it landscape, let's call it weird shape. Boom. There we go. So we'll open that file directory. So we have weirdshape.jpg, and there it is. So
That's cool.
I mean, arbitrarily we drew it.
Can you color it? Why can you just say change the color?
In Mathematica?
Yeah.
Yeah, let's Actually, I might be able to go to here and double click to edit, it says. Let's see, can we change the color here?
Oh, well, that's not
There we go.
fun.
Now, as far as colorize, let's see, color, let's see, color setter. I have no clue what that does. Color setter. I don't understand that one. Color eyes. Let's colorize this guy. We'll paste him over there. Boom. So I don't know what it did with the default values, but it colorized it, right? And if we want to see what the default values do, again, we pop over to get help, and we could see the options, what the default values are up here. Generates an 8-bit image. It scales it. The color rules are automatic for the pixel values. So you just give it an image, and then you can give it a color function. So let's make the color function. Let's make the color function this. We'll paste it in over here. Boom. There we go. We only have 2 colors, but let's try one of these. We have a moon. Boom. What are some of the color functions? Let's go see.
It seems like when you're making graphs with statistics, you can assign certain ranges to colors.
Yeah, you could. I mean, here's a color function. So a color function would let you define a function to spit out colors, it looks like. Right? So here's one.
And that's kind of cool. Like you could say, and I don't know how you would say a range of blue. I don't know how you would define that, but I'm sure there's RGB values.
Well, blue range in the color spectrum. I mean,
Yeah.
if you just look at the radio spectrum, blue is certain values, right? So you could probably just say.
Well, yeah, but how does mathematic? Is it RGB or hex?
It actually supports all those. Let's look.
Find it.
Color. Boom. Color schemes. Colors.
Boom.
Color transformation.
Sound like
Color
John
processing.
Madden.
I know, it's like, exactly. Or that chef, right? Bam! Right?
Yeah.
But yeah, so here's color processing, right? So color spaces, it's got
Yeah.
color spaces. Here's image spaces, right? So it looks like we can do all that stuff. And in this case, they just say color function is blue, green, yellow. So let's steal that. Because over here it was rose colors, those are kind of boring. Blue, green, yellow is cooler.
That is cool.
Right? So, again, I don't really know all this stuff. I've just played around enough not to be scared anymore, right?
That's awesome.
Point, click, and copy is the strategy so far. But, I mean, stuff like this is kind of cool too, because, I mean, how many times can you think of, I want to create a grid of stuff, right? And boom. Now, as weird as this sounds, I could use this grid as a random sampling. I could say my random numbers are between X100 and Y200, and come up with random numbers, and then use this, and wherever it hit, read the color value there, and then that's my color, right? I mean,
Yeah.
and I've done that before with random number generators in like C programs and stuff back in the day. And, you know, I created a little array of random colors and that was fixed, and then I would just reuse them. And so this is the same idea, right? And it took one line of code.
So
But-
you're a mathematician. Is this useful? Does it seem useful to you, or is this like?
What, in general?
Yeah, or is it?
Yeah, it's like
way?
No, I think it has a lot of stuff that's probably could be really handy.
Yeah.
Totally depends on what you're doing, and I'm not sure yet if any of my projects would be best done here or not right now. But
I've just never known any mathematicians who use mathematics. So.
I've never known a mathematician to cover.
Like, here's one, and I don't know how to use NSOLVE, but this is actually a very powerful function. gonna go to the help because we're gonna copy this because this is somewhat mathematical, right? So we want, what did I do wrong? Did I type something wrong? It's all equal to 0. Give me a break. Something I've got here has messed up the context. So let me say hacking around. Who's that?
What do mathematicians normally use? They don't use mathematics.
Oh, it just totally depends, man.
Really?
Super odd of a question.
Right.
I mean, if you're a pure mathematician, like you're not really using software. It's like theoretical stuff.
Mm-hmm.
But if you're doing applied math, it just completely depends on what
company you're doing, basically.
Yeah, I mean statistics, there's certain things that
There we
people
go.
like to use.
So because I had redefined X before I messed this up.
That might be it.
So, I mean, that was a good thing to know, because when you define stuff and then you try and redefine it and it doesn't do what you think it should do, it usually is you. So those are. I mean, I don't know whether that's something you do, but you're solving for X for that equation. Here's all the. You guys remember long division?
Mm-hmm.
And then polynomials, having to figure all the polynomials. Well, that's what that freaking guy's doing through approximations. But basically, he solved X for this equation. All the things that come out equal to 0 for all these different X's. There's a few of them. So that was kind of cool. But the cool thing is, it shows application. So for the mathematician here, we've got some applications. Find the intersection point of a circle and a parabola, and then plot it. I don't know whether you have to find intersection points in some of your problems, but I know they wanted us to do that all the time in physics.
So that shape that you drew, can you plot that?
Can you plot a shape? You don't really plot a shape, but I'll show you what we can plot that I know really easy. This is really easy, where I want to plot x from negative pi to pi. Boom. So that's a simple one, right? And then there's the 3D version of that. And I didn't give it enough values. So let's see. Let's do this. Let's go back to here. And here's some other stuff we can change. We can change the color, the thickness, whether it's dashed. Click all those things that are done. Those are all like really simple. We can make this bigger really easily. You can give it a frame, you can export it. We can do the drawing tools here if we want. So if you're doing something for a presentation and you need to point out that this is, kind of important. So this guy is important for whatever reason, you can do that. So that's kind of fun. Now, I'm going to take this, do the help. And there's all these plots here where he plots multiple equations, which is kind of cool. And then multiple, these are Bezel-J functions, which I can't remember, but I remember they were in calculus. And it creates a table of them and then evaluates them for these ranges and fills them in with different colors. But here's what we want, plot 3D. So we'll steal this one because he's already got the values in there. And you can do that and rotate it around in real time. Now this is really nice because back when I was first using Mathematica, you couldn't drag anything in real time. You had to go tell it the angle to plot it at, and then wait, and wait, and wait. Like, so this is real time. This is kind of cool.
Yeah.
But you can do these subdivision changes and all that kind of crap. Change your axes, remove the bounding boxes, change your background to something prettier, all that crud. But the nice thing is you can rasterize this so you can copy it out, one click, export it to all these different file formats, change the lighting so it's ugly, right? Back to automatic since it's pretty. But add the bounding box back in. All these things here, now that we've got this thing the way we want it to be, we can convert it into traditional form. We don't want it to just be that. Let's convert it into the input form. So there's the input form of raw numbers, right? Graphics 3D. This is like the really low level of crap to plot that ugly stuff, axes, all that stuff to plot that little graph. And you could copy and paste that into another notebook if you want it. We're not going to do that. We're going to move it to here and tell it instead of, it gives us the output form, which is the graphic 3D, which is something we could copy. Now, all these particular things, that was the raw input form. I already did that one. Sorry. I forgot I did that one already. Output traditional form. So this traditional form says take number 13 and change the lighting, right? So, boom, we get that. So now I can take all these and collapse them into what we wanted. Remember that? There was the function, right? Which is kind of nice because after we dorked with it and tuned it and changed all of our colors, we can still get back the one thing we want to copy somewhere else and execute and get what we wanted, right? So it's kind of cool. So again, under here, these things, if you notice on Plot 3D, there's a lot of options, right? And then each of these little options has things you can click on for plot styles, where you can go tune the plot styles, right? You can do things like that, or 2D versions of that, and then markers, and again, you keep going. You can go into graphics and sound and all the manipulation options, integrals, which is kind of cool. We'll just copy that because we can. And boom, there it is. But every one of these things, right, is all related to the original graph that we did, like this, right? And we can tune them. We can say, plot this, but only plot up to 0.5. So it's going to cap off all the plots points above that point. So you see those hollow spots, right? Which is kind of cool because, well, here we did percentage. Let's not do percentage. Let's do this, and then we'll come back and do that again. There we go. Now we'll take that same thing. And obviously these go above 0.5 because they go up to 1 here, right? So when we paste this, we're going to get the same graph plotted, but clipped. Which I know We used to have to do that in high school sometimes. You guys remember? Well, maybe you guys didn't have to, but our teacher would be like, I want to see the plot of this function between X and Y, right? So you'd have to figure out, and then you're solving the freaking formula like 20 million times. Oh, this one's greater than the X range you gave us, so I wasted all this time calculating this, right? Now it's one line of code, right? I'm afraid to show this to my kid because they'll get lazy at math. But at the same time, it helps you understand math more. Because instead of taking 2 hours to do all the freaking points, you can do it in 1 second and see what's really going on. What you're really doing is capping at those ranges, right? So that kind of stuff is cool.
Kind of empowers a non-mathematical mind to be able to accomplish and do and understand more.
Yeah, I mean, I've learned more math in the past 6 months than I had in like the last 25 years just by playing around. Because I could explore and try things, and failure was basically no cost, right? It's like, there was no paper, it wasn't 5 pages of writing crap out.
Yeah.
It wasn't making a mistake for not associating correctly on page 2 and then 3 pages later it's still wrong. That kind of crap. So, I mean, there's all this stuff, pie charts, bar charts, there's all kinds of crap in here that's amazingly cool. There's tutorials. I remember how I was telling you those tutorials are out here in PDF form that you can download? You can even buy a printed version, which I discourage highly. Save your money, and instead of buying all these printed versions, buy yourself an iPad or an Android for, you know, next to nothing if it's even used. Pop the PDF on there, or better yet, click the web version and you can go right into the web version of it, and you can see these same kinds of things, right? Symbolic graphics language, since you were asking a little while earlier, there's a, we can do this here. Pretty sure this one's gonna work. So it's downloading the data, so we got our bunny. So we have the bunny, and we need this data. So you click on those, and then you can copy this over, evaluate it, it'll download the data from Wolfram for each one of those guys. And we're only going to get the ones we need, but we click on it, copy it over. So, we did that one. Do this one. So it's a spiral. And now we should be able to copy this and hopefully show something. So that one's flat. By the time we get down here, after we do all these, right, we can do all these. I'm just going to see if this will plot some of them. If we just take out that doesn't have in there. So we got, those are the ones we have. So we've got those in there. Notice they're live inside that grid, right? Through these servers. We didn't load these in, so they're empty right now. Right?
So sorry, I know you talked about this last time.
Yeah.
What's the difference between having the Wolfram language ultimately and Mathematica besides the metaphor?
Okay, so the Wolfram language is actually bigger than Mathematica that you're seeing.
Yeah.
The Wolfram language is the language, on which Mathematica is built. So the stuff you're seeing me code over here, this is the language. We're using a notebook to write the language and get the output into the notebook.
Okay.
But this stuff actually is the language.
So the language come with some sort of IDE or?
Well, so there's multiple ways to think about that. There's the command line IDE, because you can write, you know how you write bash scripts with pound bang? You can do the exact same thing with Mathematica scripts, right? And I'll try and show that next time, right? Because I can't remember the exact syntax, but you can pipe them and all that kind of stuff, right? Notebooks.
It has notebooks as well?
Well, when you get it with Raspberry Pi,
Yeah.
when you get the Raspberry Pi, you have the Wolfram language and you get a copy of Mathematica.
All right.
So you have everything I'm showing you, it just won't run quite as fast. And you can't do anything commercial with it, right?
So it's
And it'll be-
restricted to running on that Raspberry Pi.
Yeah, when you do it, it'll license you and it'll let them know at their servers, right? But it runs in X Windows on the Raspberry Pi, so you'll see the same kind of notebooks, same interaction that you've been seeing me do, and you'll see the same output. You'll be able to change the fonts, everything. But if you want to, you can go down and write Mathematica scripts and run them on the command line too as Mathematica scripts with the Wolfram language. But the Mathematica that you're going to see on the Raspberry Pi has full access to the whole Wolfram language, which is, there's more functions than I can show you here.
So the Wolfram language has functions that are not recognized in Mathematica?
In Mathematica 9.
No.
Because the Wolfram language that's on the Raspberry Pi right now and the Mathematica that you're running on there are what they would call betas of the Wolfram language in Mathematica 10. They don't call it that, they just say it's
Okay, but
Mathematica.
so I still don't understand if you can evaluate any function inside Mathematica. Is it just a front end to the language then?
It is. The notebooks and Mathematica that you see here,
Yeah.
all this stuff you're seeing is just a front end to the compute engine. I'm gonna show you that. It'll make more sense now. See these? There's a notebook kernel, and then there's the compute kernel, which is the default. And then there's concurrent config options, and then there's, in this case, there's no parallel kernels. But see all these other kernels running? Each one of those is a process, and I have 8 because I've got the commercial license, and there's one for each hyperthread, right? So the notebook is running against one master, and that master can distribute out. If I did those parallel functions, they get distributed out to all these other ones, right? So if you run the command line scripts, it'll still hit the compute kernel. If you're in the notebook will talk to the master kernel and distribute out the kernel.
So maybe I'm not understanding why notebooks are so cool, but
Well, the reason notebooks are cool is because usually when you're solving problems, if you can do it in an exploratory fashion, you're gonna.
but that's kind of how I feel when I'm a Python interpreter.
And Python interpreter is very similar, right? And anything that has a REPL, read about print loop. And Python, when you're an interpreter, is exactly that. Ruby with IRB is the same way. Clojure with its REPL is the same way, right? You try something, the evaluator comes back, you get your feedback,
So that's what you're
ready.
All right.
And notebooks are exactly, they're a REPL, but they're a little bit more powerful. And Python notebooks actually got their idea from Mathematica notebooks. These have been around since Mathematica 1 in 1989, or 88 actually. So the idea is not new here, it's just the Wolfram language still uses this, right? So that being said, I'm going to show you one more thing before we get ready to go.
Yeah.
This is just the beginning, and it's an untraditional intro to Mathematica because it's trying to be a more hands-on group. And hopefully you guys have Wolfram language next time when you get to come, right? I'm hoping, because I want it to be where we actually do kibits and we show each other stuff more. But if you are a programmer and you actually want to do real giant programmery things, there's this thing called Wolfram Workbench, which is built on Eclipse. And to your question, what's another IDE? You can go in here and you can create notebooks, or you can create source files or test files or packages to write your code, right? And you can debug and single step through it and all that kind of stuff. And it has the same things of what is the Wolfram Workbench look like, what does my code look like, what is debugging, JLink lets me
We
call.
get that with the Raspberry Pi as well?
No, you don't get this one, Raspberry Pi. This one's commercial version has it. The home edition, you can get it as well, right? And the home edition is $295, but if you're a student somewhere, literally what I've told people to do is go to ACC. No, go to ACC, sign up for continuing education or something, like $100 class or whatever. Then buy it.
Yeah.
Save yourself $200, right? Right. You don't have to go to the ACC class, but you can buy your copy of that. Right. Save $200. But anyway,
I need to run.
Yeah.
Yeah, it's great.
Thanks for coming.
Thanks very much. Guys.
Yeah, next time, hopefully Mathematica 10, Wolfram Language are out, and we'll have the Raspberry Pi next time, for sure. The reason we didn't this time is because Norman was going to be out, he had an unexpected trip, and he wanted to make sure and see it, because he has some stuff he wants to show as well. So,
Sorry for everything, brother.
thanks.
All right,
Have a good one.
Yeah.
Thanks for coming again. Appreciate it. It's always good when people keep showing up. That being said, you guys are all new.
Well, I work
So,
here, so
right.
I'm just kind of always.
So you missed the spiel last time.
Yeah.
As we're learning this, everybody, I mean, you saw me just cut and pasting things, but I knew enough to change stuff because I played around with it.
Mm-hmm.
But what we're looking for is, because everybody's pretty much a beginner, one-liners. If you learn something new that might help somebody, just bring that, show it, take 2 minutes, just pop it up. We'll either have, you can bring your Raspberry Pi and we'll jack it in, and you'll be on these TVs, or you can bring your notebook on a USB stick and we'll pop it in and we'll show it on one of the laptops, right? Because we want it to be really, your projects, the things you care about are the things you're going to want to work on. It's going to make it exciting for you. But as you learn little things, even about how to use the tools, you can show 1 or 2 liners and share that. It'd be awesome. Because I think it is so different. Like, I mean, what you were saying earlier is there's so much stuff and the data, all these data sources. And what we saw is not even the tip of the iceberg. It's like the gnat is on the ass of this gigantic continent of Mathematica in a sense, right? I mean, there's so much stuff there, it's incredible. Like from a math point of view, you can take R code and paste it in here and quote it and put it in an R evaluator bracket, and it'll run all your R code and you'll get the output, and then you can use all the Mathematica features to take
That's
the
pretty
results,
neat.
right? And there's a video of that on the site, so if you're interested in R, then check that out. For big data people, there's a Hadoop link. So you can use Mathematica to call out to your Hadoop data stores, query the data stores, bring back the data and process it inside of Mathematica for what Mathematica does best. It has full access to MySQL and Postgres databases. So if you have databases, you want to query them, it'll do it.
Does it work well with MongoDB?
There is a Mongo adapter that somebody outside has done as an open source thing. I haven't tried it yet, but through the REST API, Mongo has a REST API. The Wolfram language has REST calls. So you can just call it, and get back your data, and it knows how to
So you can
process JSON.
configure Wolfram with.
Yeah, you can hit
almost
anything.
anything.
Yeah. I mean, it literally
It's
is.
just choice.
All I can say is go to the website,
It's interesting that
watch
you
all
call it
kinds of videos.
a knowledge engine. What's comparable as far as, say, you have a portal or a hub and you want it to be able to calculate, dynamically and in real time, maybe supply chain issues or fluidity. What compares to this? What would be Mathematica's competition?
Well, all the competitions that I know of are like commercial products that are specifically for that. They've been written in either Java or something else.
Right.
And they expose web front ends, through either JSPs or whatever, right?
Mm-hmm.
Mathematica is a general purpose system.
Right.
Computation, both from pulling in data that's from Wolfram Alpha, which is the structured data, your database is your Hadoop, JSON data sources, files.
Right.
Like, let me show you one more thing real quick, because if you guys get the Wolfram language, you'll wanna see this, and it's straight in the documentation, so I don't actually have to do anything weird. If you go up here, how-tos. This how-tos section has got tons of great stuff. All these things at the beginning are like little core language things, how to create variables and functions, right? Make tables. But then you get down into here, how to do some really cool stuff with graphs, right? And each one of these is like little tutorials, and they're short and they're sweet. But then you get down into here, data manipulation, import from a spreadsheet. You can load in an Excel spreadsheet, it knows how to do that, right? Make your own tables. Calculate basic statistics, right? And again, all these things you can plot, right? You can do a ton of stuff. But this is one I love. Clean up data you imported from a website.
Mm-hmm.
Clean up data you imported from a zip file, right? These two were like awesome because I click on that and I go out and I say import from this site all the things that are tagged with elements. So there's a class or the ID identifier, elements, is going to grab that. In this case, it's probably a table, right? It pulls that data back, and then we can look at the data, right? Here's one they imported the US Census data for foreign trade balances from some year. And here's the data, right? And then they go through this example and they show you how to write short little tiny programs that say, give me everything out of this data we just pulled in that's numeric, right? And give me that back. So this is all numeric kinds of things, right? And it shows you how to pull those data things in from a website. Step by step, it goes through and shows you, like, here's a function g of x. If it's a string, and then if f of x is a string, and give me a number string, right? Convert it to a number, right? So it checks the type. If it looks like it would be a number, then it'll convert it to a number, right? Anyway, it shows you how to clean this up and take it from a website and turn it into Mathematica data by the time you're at the end, and then you plot, right? And this is a perfect example of things people need to do day in, day out. That if you had to do this in something else, you'd probably go to the website, copy and paste the table, paste it in Excel, and then go change the column types and all that kind of stuff, right? Whereas this, you could generalize it and reuse this program. But anyway, then it goes into some of these other tutorials, how to deal with patterns. Like you're looking for patterns in data or a text, right? Let's say you're reading in stock data and you're looking for a pattern. Give me everything that's Apple, right?
Mm-hmm.
Shows you how to do, and it's almost like a regex, but you can treat it as a stream of data, right? And Mathematica has cron jobs, it has everything you can think of, timers, so you can have your little program run every hour, right? I mean, it's all in there, it's just there's so much, you may not stumble across
like you
it.
basically have to hire a scientist to tell them this is what I want done, and they'll go in there and do it.
Or you get it for yourself and you just poke around, because, and that's why I was trying to stress at the beginning, the documentation, all these examples, I have not run into anything, and I dropped out of college, right, to work as a programmer. I got a job, and this was way in the 80s, so it was easy to get a job back then if you knew anything about computing. And so I got a job, and I was like, I have not found anything in the documentation that if, even mathematical equations, that if I didn't look at the examples and follow the references, because it has references to like the real deal, right? And between that and Wikipedia, there's nothing I haven't found that I couldn't figure out. And that's like, wow, there's a ton of math I can't even freaking read in these research papers, but I can take that equation and pop it in here, because that was one of the other things I didn't show you. They have the math palettes where you can actually type in your equations. Here's like the square root, and then the advanced things, and you pop them on there, and you fill in the parts that need to make sense to you, right? And then you click on these each individually and fill them in, right? So you can do that. Now, I'm not out there doing things like financial quantization formulas and all that crap. I'm like doing some stuff and helping my son with his high school algebra and crap. But at the same time, it's like I can look at certain papers and know that I can punch them in here, and then I can take those functions. And the nice thing is the functions look like real math. But if I did that thing full form, right, that he showed in the video where he said full form and it was sine x, blah, 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 and then it decomposed it and it showed you it was plus was the function, right? So instead of 2 plus 5, right, and I get 7, I can say full form, right, and say percent. I need a bracket, square bracket, right? Now in that case, full form of percent was 7, but let's do full form of 32. Percent 32, sorry. Is it 32? It's 32. Okay, so I'm an idiot right now, so I'm just going to do it the hard way. Okay, I'm doing something wrong. But anyway, you can do this, plus 5, right? If I look at plus, it's actually what the system interprets plus to be, right? So you can see plus 1, 2, 3. And this is one of the cooler things too. You don't have to worry about infix anymore. If you want to add a sequence of numbers, you just call the function plus on it, right? So it would be the equivalent of, in Lisp, you would write it this way, and without the times things, because I'm in space. Plus, and it would add all the numbers after it, right? But in Mathematica, you just say plus and give it the list, and it'll add all those numbers in that list, right? But if I say, let's see if this works here. Should. No, it's just giving me the result, because the result counts. But anyway, you can put full form in there. Actually, why didn't I just do this to begin with? Full form. There we go. So full form of this full form of that is this. This is nested, right? X over the square root of 5, right? So this is the pretty that we can do from over here. Or if you want to write it a programmery way, you can do it this, right? Those are the same things. And plus is just a function. Divide is a function. Multiply is a function, right? And they take multiple arguments. But anyway, all those things you have at the power of your hand, and because you got the documentation like I just did over here,
Right.
boom, right? And every one of these has an application, right? Where does it make sense to use this, right? possible issues you may run into properties of that particular thing. Here's a tree form. I mean, this is like pretty wicked cool,
Yeah, that's cool.
right? X to the power of 2, a plus b to the power of -1, all that times x plus the power of 2, right? So you can graph, that's another thing, you can graph so much stuff. I mean, there's just crap loads of stuff in here that's, you know, it goes on and on and on. Tree forms for all kinds of stuff, right? This is the tree form for this graphic. And this, they did it a shortcut way. The // is another way to apply a function. So we applied, and this is showing you all the commands that it took to create that little graphic. That's one way to decompose it, right? So,
Good.
I mean, and then you can operate on this tree like it's a program too. I mean, it's all there. You can ask it for the attributes. I mean, all that stuff's in there. And I jumped around, but the reality is if you start here and then how-tos and core language, those are your places to start. And core language literally starts with a language overview. And there's learning resources for tutorials. The syntax, somebody was talking about, was kind of a little weird earlier, but it actually is really regular. And it makes a lot of sense after you get used to it. And it only takes a little bit to get used to. It's just, I hop around between my day job and this, and so it's like, okay, the ampersand I completely forgot. Meaning 4 types of brackets, the square, the squirrely, angle. But these are always there. This is always online. You can have a notebook open on your Raspberry Pi, and this is sitting right there too, right? And then these how-tos, you literally do exercises, how to work with these lists, how to create a list. And
It comes with Raspberry Pi, but would it also work with like a Zigbee or other Arduino boards?
Right now, the Raspberry Pi is the first one they ported to. The next one they're doing is the Intel Edison, which is the same size and slightly thicker than an SD card. Right?
Really?
So it actually looks like an SD card. It's just a little bit tall.
You can have the language and the mathematic
Yeah.
in that little thing.
Yeah. Yeah, and to give you a context, Mathematica, when it originally came out, it ran on a 68,000 on a Mac. And then the first time I used it was on a Mac, and then the next machine had it on a 6820 or a 30, 68 or 30. So, and that's why the Raspberry Pi is actually faster than the next machine I had that was 10 grand in 1989. But it's 100 times slower than this.
Yeah.
Right. But it's more than fast enough. Like literally, you take the Raspberry Pi, you plug your HDMI into your HD TV, and you plug in a mouse and a keyboard, a cheap USB mouse and keyboard, and a little 5-volt power supply, and an 8 or 16 gig SD card, $29. And it's a full Linux box, great.
Yeah.
And it's like, boom, I mean, it's fast enough, you're gonna type stuff
You
in.
can put it in your phone and do it up here.
No, not yet. There's a Wolfram language, the playback mechanism that he was talking about on that cloud piece.
Mm-hmm.
They're putting the cloud player for the mobile phones. So you'll still develop on a Raspberry Pi or one of these.
Right.
And then when you publish your solution to the cloud, people with the phone will be able to run it. Or if you license the embedded version, you can embed it in your phone app. Like if you create a native app and you want Mathematica charts and calculations, you can run the embedded version. So those are the 2 options. So.
Let me ask you one more question. So
Yeah.
I wouldn't know how to accomplish it, but could Mathematica like basically have a character recognition function as far as a PDF and be able to turn that into actual text and cross-reference it maybe with other PDF text, things like that? I guess the initial step in that would be turning the PDF into text.
Yes.
not an image.
Let's take a look.
I actually have to jet, guys, but thank you
Okay.
so much. I appreciate
Yeah,
the
yeah. Hope you come back.
interaction. I plan
That'd be
to.
great.
And that Raspberry Pi, I've heard of it. I think I'll have to check that out. It might come in really handy for some stuff I'm trying to do.
Yeah, it's definitely. I mean, it's the cheapest way I know of. $35, and
Yeah, it's
a RAM
ridiculous.
card and
Yeah.
a couple of cables, and go to Discount Electronics and buy like a used keyboard and mouse.
Yeah, exactly. Or the Goodwill computer store.
Exactly, same deal. Yeah. Thanks for coming again.
Nice to meet you guys. My name's Emerson.
Emerson.
Yeah.
Hey,
Nathan.
Oh, Michael.
Hey, Mike.
post to the meetup boards the discussion that as soon as the Wolfram language ships, I'm gonna start actually posting more to there.
Cool.
It just feels weird to post stuff when nobody can actually try what I'm gonna post, right?
Yeah, it's a little
So
tricky.
definitely as soon as that pops out and you grab a Raspberry Pi.
No, but this is a good way to like start. So.
Yeah, and I mean it's definitely richer than some of the other ones out there, Maple and R and stuff. And the Wolfram language, like I said, has even more stuff than what I can show you here, function wise and stuff. So even richer.
All right.
Anyway, thanks for coming.
See you later.
1 fish, 2 fish, red fish, blue fish.
So there was a recognizer working. So I'm gonna make this graphic bigger. That's actually a graphic. And there's a text recognize function.
And then it said
It looks at that graphic and then we told it to speak it.
1 fish, 2 fish, red fish, blue fish.
Okay, so I'm gonna go out here and I'm gonna go billboard.
So it recognizes text. I mean, can you speak into it? Does it recognize voice and turn it into text too? Can it already?
I can't remember if it does that, but we'll check in just a second. We'll try an experiment and just see.
Because I saw that sound category on that basic main page.
Yeah, let's copy this. Go back. I'm gonna copy this image. I'm gonna go back into Mathematica here because not every image is gonna be recognized, right? It's just the OCR is gonna be tough, but let's see if it works.
Repairs. Cent equals cent n equals 1 equals 1 equals.
So I got something else out of there, but it got repairs.
Right.
So that's kind of a tough picture to do. So let's see. Let's see if it can do this one. This one's kind of weird.
just wait for when you can make it speak what is like to describe the image.
Yeah, I don't get it.
Om you om, pour a giant thirst.
Yeah, they got a giant thirst. That's pretty good.
What's going on?
We're doing some recognizing.
My shift is over, so I'm about heading out. Any of you need tickets for?
I need one for downstairs. Yeah.
I'm not too concerned with all you guys. I doubt. On Sam's watch, I doubt anything bad could happen here.
Nah.
Shut the whole place down, huh?
Yeah,
I'm here. The windows all are gone.
Yeah, they close at
They
night.
took all the copper piping.
But yeah, we'll be done in like 2 minutes, man.
No. You take your time. You guys welcome to sit as long as you need.
Okay.
I'm not gonna be.
Thanks.
I'll get you a ticket. I just wanted to let you know that I was heading out. Mike was
Okay.
there too, so it's not.
Okay, cool. So the text recognize, and I'm going to take you over to the help, because it does have help. There is actually neat examples, which you got from there one, right? But you can paste in other graphics, right? Like these. And these actually work. You can give it entire paragraphs that are styled. Thanks, Ian. Appreciate it. That are styled, and it'll recognize them even with multiple columns. Now, it doesn't keep the columns lined up, but it does recognize the text, right? And then you can say, some other options. Which language is it in? How to use the right recognizer, right? Russian. So there's some of those, and then you want text to speech. I don't know if it does text to speech.
Well, speech to text. It just did text to speech. Speech to text, and also, I guess text to text, I guess it would see the image and be able to format it, but
speech to text, I don't think it does, because that would be voice recognition, really.
right.
I don't think it does that. It does the optical character recognition, so.
Which is really, really cool.
Yeah, I mean, for like, I mean, for me, it's part of it is remembering back to when that was like a research project, and now it's built in.
Now it's a consumer product.
Yeah, it's like, holy crap. But yeah, there's tons of these. You can play music. You can play individual notes.
Oh, really?
Right. Yeah. So here's it'll play a C and a G. Forgot to put the S. Didn't copy the S. So it rendered them.
I think I have a question for you.
What's that?
Random question. On Wednesday, they were looking for someone to stay for that, but Grand Marnier, the album, they're going to be shooting an ad up here.
Oh, really?
So they're going to be doing from like 9 to 12, so I don't know if you would be interested on it, like on a personal level as well. Sitting in.
What responsibilities would I have?
You just have to watch over them.
Well, yeah, totally.
And then you basically just watch over them, and I can let Sarah know that I talked to you about it.
On Wednesday,
Wednesday
9 to midnight?
9, yeah, they're just going to be filming, and yeah, they were saying, hey, they might have like space for extras as well, so you might get that in the ad if you
Right
want.
on, man.
You can get some free booze.
Cool. Liquor now.
Yeah, right. The cord out.
There you go.
Maybe I'm sick on that stuff.
So that one was like weird sine waves, right, from this equation.
Wow, that's cool.
Right, and so here's another one. I mean, these are just like incredibly. That's that visualized.
That is badass.
Yeah, I'll make
That,
it bigger.
I'm sure like experimental
That's
musicians would love
That's
that
this.
stuff.
Yeah.
So you could like represent any visualization, well, not any, but any visualization based on data or graph or plotting in musical notes.
Yeah, you could take data and play it. Right, that's exactly what we're doing right here. We're just taking data and playing it. Like, here's a recorder sound. La 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 la. So we did that. There it is. We just recorded our voice. La 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 la. So then we can do, we can modify it, squish it to be 8 seconds in this case, right? So now it's only 8. It's
Nice.
right, 0.8 seconds. Here's some neat examples. Just copy these. That was just random, right? Random choice of a piano, a cello, or a tuba, and a random integer between 12 and 30.
So you could put pop songs that you take the top 40, put it in there, and tell it to recognize how many patterns of notes are held for how long, or which melodies are repeated.
Yeah, I mean, you could write the code to try and do that. I mean, it might be harder than just pop it in.
Most common melodies. Oh yeah, it's not gonna be that fast, but just the thought that you could do that,
Yeah, I mean, it's
And I guess you could do it before, but
randomly generated right there. Right? So emit sounds, play. I mean, those are all speak. Here's the speak command. This is close to what you wanted, right?
This is some text. Thank you.
Let's speak this.
Cosine of x squared plus sine of x squared.
I mean, pretty wicked.
Could you have a doc, like a text doc pulled up and be able to have it speak through Mathematica by clicking it over there or something? Because it would be outside.
Well, you probably copy the text into Mathematica and then let it speak it. Maybe make an HTML thing where when you click on a paragraph, it sends a message to Mathematica. Sends it to paragraph content. Like this one actually has column 2 as a button and it speaks the value.
2.
Right?
2.
The number 2's defined, right? There's some more neat examples. So we got split it into substrings.
The list 1, 2, 3, 4, 5,
So it's reading this.
5 elements, 12, skip 14, 11, 13,
So yeah, we told it to take some out. Pause. So you can control
15.
You can control how the speaker phrases things, right? It's kind of cool.
well, I have a lot of exploring to do. I mean, there's going to be so many to get started. You know,
You almost have to define what you want to do with it to even know
yeah.
how to explore it. You know what I mean?
Yeah. I mean, here's the code for this graphic. That's just the code to create it right there. Here's a graph plot. I mean, this is kind of, if you have anything that's, and a graph is a data structure, right? It's just edges and nodes, like cities on a map and the roads between them. And they just created some graphs with different numbers of nodes, for up to 102 for.
So you could feed in like different data sets, like public public domain data sets and stuff. Like
Yep. So here's a graph, right? Created a table.
Like, could you like take a Google Maps image, okay, say like a moderately rural area, and have Mathematica interpret like maybe like rural roads or pathways. I mean, identify between like trees and brush, which is more clear, and have it show like that kind of graph.
Yeah, because you'd be doing image analysis to recognize where the roads were and stuff like that. There's actually one example.
Or like trails and stuff, you know what I mean? And
yeah. Like here's one of the maps that you can get just real. Now the bold bar means it's still evaluating, by the way. So here's a map, we got it from their data set. And we colored the dark terrain, right? But you can do similar kinds of things with other maps, right? Get other data from them, right? What projection it has. Because all these maps have all kinds of data associated with them.
Right.
Right, depending on the file format. And that's what these other things, they got the datum, they got the projection, the spatial range, the elevation range that it covers. This map here, all these attributes of that map, right? So, and there's other ones. Here's another map format and the different stuff it shows. Right. So you can do, you know, there's all kinds of different GeoTIFFs, right? Really old black and white ones. There's just, I mean, just tons of them. It's like incredible stuff. I mean, I just am like blown away all the time. Here's all the different formats and everything. KML is what you can get from Google.
KML is what you can get from Google?
Yeah, that's usually for map data. See, there's one right there. Right, that's the weather in KML format. And then here they just said, give me the graphics list of all the little dots that were on here for the cities. Then you can find out the layers. And then from that same data, you can grab the populations for each one of those cities in the region and the elevation and plot. Here's the shortest path to some of those cities from up here. But you can do the same kind of thing to find, you know, roads and stuff like that, right? So,
so basically it's only limited to what data sets you put into it and how well you know how to model data or extract relevant information from that data. No matter how big it is, it could be a whole bunch of stuff, it doesn't matter.
Yep. And like, here's some of your stuff that you were talking about. Here's analyzing road networks, where the networks are already put in. So we already have the network laid out of this city that's in Champaign-Urbana in Illinois. But they take that and analyze the roads, intersections, and stuff like that, right? So, and you can give certain criteria in this area, and it'll show you those streets, right? So that's one example of image analysis. Here's another one that's kind of really cool. This one actually is recognizing blobs on this that don't overlap, right? See, these overlap, but these are all the ones that don't overlap.
And it's recognizing that.
Yeah, right here. And this is the equation for identifying the cells, right? And then here's the circles that you draw on top of them, so you create all the circles.
Okay.
And then you actually show the cells with the circles over top of them. But here's the equation for selecting the cells, right?
And so how easy would it be to adapt the equation showing this separation of cells, reverse it to showing the overlapped cells? Would it just be
I honestly don't know, because I don't understand these equations specifically.
Right.
But
it's not impossible.
It's not impossible, but like here, like they binaryize, which means take values, every pixel value or whatever, and map it between 0 and 0.7, right? And then delete the border components around it. We'd have to look up what that means. And they're looking for areas and holes, where the first argument is greater than 100 but less than 1,000, and the second argument is greater than 0. So what I'm thinking is these holes inside here, and then these black areas mean there's something like that, where if they also then come back out to a color value that's the same as this hole in the middle, that then they know they have something that's not an overlap if they find that all the way around. Right? So you do stuff like that, right? And then there's edge detection, which we saw in the video. They've got all that kind of stuff. But here's more on image processing, right? So, which we were just looking at. Here's, they took this and they colorized it by applying some image transform. And this is 13 pages worth of examples, right? So there's not just simple ones, right? Color transforms, motion blur effect, stained glass effects, right? Blur, edge detect, divide images around certain features. So here's the input image, and then we use the Gaussian filter Laplacian with a distance transform of 2 to find the borders of where these things are, right?
It looks like it
We partitioned them pretty
turned it
good.
into different regions.
Yeah.
Based
Around
on
there.
whatever the,
Yeah, around their features.
yeah.
So that's like a good example you can start from, right? You could start from any of these kinds of things. There's like one I just skipped by, which is pretty cool. This one's actually pretty neat. You can erode the 3D volume. So you look at the 3D part, and then as you erode it, you see parts that will disappear based on that function. So related to the density at a certain point or something like that, right? Now I'm not sure how that works, but there's an erosion function, and we could look that up and see what it does. Right.
But the cool thing about it is you don't have to know what every function means.
Right, you just have to figure out enough to know what to expect and whether it's going to do what you think you need.
And then if you want to be an engineer about it, then get really specific.
Right.
Yeah.
Like airspace detection. I found some faces. Find faces is the function. Right. So that's it. Yeah. And you can tune that. Extract larger objects, extract things in focus.
Right, and I bet if you have something that
This one's cool.
is a better face detection tool, you could still
Yeah. You
Put it
could
in
call
there.
out to that. Yeah. This is cool. Find the matching points on 2 images. Even though they're different sizes and they're rotated slightly differently.
Mm-hmm. It still finds a point.
Right. See, here's the bottom here, and here it is over here. Still found them. Using imaging differencing. Right? And numbered them. I mean, that's cool stuff. Like, blows me away. Sometimes I feel like a complete idiot when I look at some of this stuff. I'm like, I made it out of high school, but how could I? Right? So here's one. It's close to what you wanted to do to identify the roads. Right here. This is to identify a river.
Oh, you found it. Yeah.
And this does it
Stuff
in,
like that.
does it in green.
Yeah.
Right.
We just have like I keep referencing Google, basically Street View, where you actually
Yeah.
see the terrain,
Right.
and it can just outline based on what you just showed us about circling around the dots that were not overlapped. It'd be
this green part does.
Colored
It's finding a river based on this little selected components with this morphological components. Color negates the image by 0.82%, it looks like. Length, -1. Do an image apply of dilation of the river. Masks it out into green, so it detects the river. Right. I mean, 3D volumes it can find. It's kind of cool. Bones. Right? So here's the 2D or 3D input, and then it finds the bones in there. Colors each different one. Similarity graph of these pictures and how, what's their distance on Earth from each other. That's what it looks like. Create a distance table, a temperature table, and then a matrix. Then you plot them. Right? And these are places on Earth with their relative distances from each other.
It's just a whole new way of thinking about things.
Yeah. I mean, think about all your photos that have GPS coordinates on them now.
Yeah.
Just feed them into this and it gives you a little graph. It doesn't even have to lay it on a map. It's just you got a graph, right?
So it's almost data alchemy. Like you can take different sets of data and turn it into other sets of data.
Yeah. I mean, here's like finding the edges of a flower image and some of the other things, right? Extracting it out, masking it. mapping the image onto some different shapes and a mesh, right? And this is just in the image analysis section, right?
Right.
Here's a custom color function. So here's the original input part, which looks like a 3D printed part.
Yeah.
Piece of plastic. Then they colorize it. Somehow they know to make these things different colors based on something. I guess
Just
it's
as
related to
bad.
how dark it is, right?
Yeah.
So here's the game of life. 3D playing out over time. Through 500 iterations. Looks like I have a glider going off the screen. But it's kind of cool.
Is there anywhere just to go pick up a Raspberry Pi? You gotta order it online.
The easiest way is to order it online, and the place where you can go.
Like Fry's would have one or anything like that. Or...
Not that I've seen, but I mean that will get it to you in like 2-3 days. But anyway, you go straight to wolfram.com and click on this. It'll take you right there,
Mm-hmm.
and then you click that, and it'll take you right there, and you can download the OS, and then that'll get you the OS for when you're ready. They have other OS installs, but you're gonna want Noobs because that has what you want in it. It's all there, and then you can go and buy a Raspberry Pi from multiple places, but and it's Raspberry Pi. I always forget the P. You can buy one on Amazon, and they have little kits, which are kind of cool because they give you the Pi and a little box and the power supply, some LEDs and a breadboard and everything.
Mm-hmm.
Because one of the things, if you watch the video on the Wolfram site back here, there's a video in one of these things on here where they show the Wolfram language sending the output from the GPIO port and then flashing the LED off and on. And then one of the other experiments somebody does is they have a temperature sensor. And you can buy these parts for like 50 cents or $1 at a Radio Shack, or a light sensor, right? So the light, you cover it up and it feeds to Mathematica and the chart goes up and then down. But you think you could hook it up to your water hose and water your grass, when the sun comes up for like 20 minutes and then cut it off, whatever, right? So there's all kinds of little experiments like that. And on this page, these are some of the first 4 that you can click to, right? Check the weather, right? And it actually walks you through exactly what you're gonna do, how to build it up, what code you're gonna type in, right? So, and there's a good community on here for this stuff.
So Mathematica is not really similar to any other programming language. It's like its own entity, or just derived from.
Well, Mathematica is the
C or
tool
C++.
you use to code in Wolfram language. Wolfram language is really the closest thing I can compare it to is Lisp. Lisp is a symbolic language as well, and a lot of the other languages are thought of as declarative. In other languages, you really have your base types like integer and float and string. Mathematica, you have those, but for the most part, you don't think about them as base types. You think of everything as a symbol. I've got X.
Like math.
I've got a graphic. I've got a chart. And you think about the things and then the functions that you can apply to them.
Right.
Right? And like in Mathematica, you have a for loop, like you would have in Python, but most of the time you'll map. You're gonna map a function across a list of values. Right? So map is even across a list of integers, and then you'll get a result of all the ones that match is even equal true, right? So instead of looping and then if current item is equal to, or divided by 2 is mod 0, right? Get no remainder. Then put it in a collection. Instead of writing all that code to do that, you just say map. And behind the scenes, it creates a collection and
Does
everybody
that
matches it.
have a memory benefit? Like you say, Python loops and this maps. Is there a benefit to just mapping as far as memory and bandwidth?
Well,
things
there's
start happening.
it's easier to parallelize mapping than it is imperative looping. But there's trade-offs both ways. You know, it really comes down to, as you get further into it, there's more intricacies around. Is your data mutable or immutable? Meaning, can it change? Or is it, once it's set, it doesn't change, right? There's all kinds of stuff like that.
Right. That's for the next class.